Is this the third part? Okay, good afternoon, everybody. We'll allow everybody to sort of join and get in the room. A few people's clocks might be running slow and fast, so we'll allow for that sort of discrepancy. Right, I suppose whilst we're waiting, I can take you through a little bit of the housekeeping. The webinar is looking to last about 30 minutes, so as sort of stated, please submit your questions, and we'll answer them and follow them up with a copy of the webinar. I'm Don Slope, and I work for Kabula. Kabula helps businesses big and small with the end-to-end advanced analytics and cloud-based data management. As you're probably aware, we're looking to do the webinar on applied AI in manufacturing, in the manufacturing industry, and we'll be touching on machine fine-tuning and automated quality detection. Okay, with me I have Adam from A-Look. Hello, Adam.
Hi, Don.
How are you doing? Well, I think without any further ado, take it from here.
Wonderful, wonderful. Can you hear me well? I hope you do.
Yep, no, sounds good.
Okay, so today's topic is applied AI in manufacturing. So let me briefly introduce myself and A-Look Analytics, what we do before we get into the topic of today's talk. My name is Adam. I'm from A-Look Analytics, which is a data science boutique firm. We build all solutions for our clients across industries. We work a lot with the retail banks, e-commerce businesses, HR tech, and also, of course, even manufacturing businesses. I'm gladly that we are also a very proud data science partner of AI in manufacturing. So for those of you that are not that familiar with manufacturing industry, there are three main reasons that we see that AI is perfect for manufacturing business. First, that in manufacturing business is very, very performance oriented. So due to the high pressure on delivering high quality with as minimal cost as possible and deliver everything in time. And the second reason is that thanks to the Six Sigma and Lean programs, there are clearly defined KPIs and business goals, which is not entirely the truth for the other industries that we are working with. And the third reason that is the most important for me as a data scientist is obviously that there are large amount of truly hard data. Those data are robust and reliable because they are very often coming from physical measurements like temperature or pressure or humidity and stuff like this. There are also reasons why AI is successful in manufacturing. And this is really a cutting edge of what the leading manufacturers are doing right now. So first of all, thanks to the advancement in the computational power and the algorithms and new ways how to solve standard tasks that are related to images and unstructured data, there are many tasks where self-learning AI proved to be superior to human, or is at least equally well performing, but is operating in a fraction of cost. Those tasks are typically either highly repetitive, but not identical. If they're identical, you don't need AI, you just need a rule. So highly repetitive task, or a task that involve dealing with complex systems with a lot of data flowing in, which is very difficult for a human analyst or an engineer to find some signal manually in the data. So today I'll be speaking about two case studies. Automated quality control and AI-based machine optimization. Now, these tasks or these projects or case studies are absolutely critical for any maker. This is what the manufacturers are dealing. It is not a tiny pilot. This is really mainstream or the core of their operations. So it's absolutely critical for them to get this right. And we have successful projects implemented with our satisfied clients. So I hope I can speak about those two case studies today. First one is automated quality control. Okay. So in manufacturing industry, where you have a lot of components that needs to be combined in many steps together to form a final output, it is absolutely critical to have checked all the components and make sure that all of them are in an okay shape, that there are no defects, no scrap. You just need to make sure that everything you are manufacturing or you're putting together is in a good shape. So the lean way to do this is that you check the quality right after the component has been produced. And this is the reason why, for example, in automotive headlight business, which is the industry or which is the case I'm talking about today, a lot of people are dealing with quality control, because they are checking quality control of every component that has been produced in the factory. In the industry, it is not uncommon to see as high as 50% of workforce dealing with quality control. So the costs are enormous, as you can imagine. Is that the quality is, or the accuracy of the quality control is not that high when done by human workers. The reason for this is that if you're asked to inspect one component, you will probably do great, right? But if you have to do this 2,000 times over 8-hour work shift, 5 days a week, you'll lose attention. Every one of us will do, and the accuracy of the quality control will decrease. And it turned out to be one of the biggest advantage of AI, that it just doesn't lose attention. So it is constantly equally good. So the solution that we brought to this problem is a smart cooperation of AI and human experts, where we try to leverage the strength of both and build a solution that will be robust and flexible at the same time and solve the task at hand. This concept is very often called semi-supervised learning. We start with unsupervised learning, then we ask experts for feedback input, and then we run a machine learning algorithm to detect whether the piece was okay or not. And we iterate and constantly improve the algorithm, because it's self-learning, and the accuracy just go high in time with more and more observation going through the system. And I hope the advantages will be visible throughout the process when I will discuss the individual steps. First step in any data project is data collection, right? So in this case, because the quality control is very often done visually, it involves images. So first step is to be able to take images of a component that have something that is called separability potential, which is a potential to distinguish okay parts from not okay components. So this is always not necessarily an easy process how to define what images have this separability potential, or what set of images have this potential. But we have process in place. But I won't talk about this during this talk, because it is not the main part of what I want to talk about. So an example I'll be using is a component that is called a light guide. It is a piece that is part of a car headlamp. That's the piece that is creating those nice shapes of light that you can see in the modern cars like BMWs or Skoda or Audis. Example of an OK component is visible in the left image. In the right image, you can see that the component is not OK from the functional perspective. The reason why the component in the right is not OK is because of this tiny black dot that is framed by the red box. As you can probably imagine, to check the quality control of a component is not enough to check one image, because these are 3D objects. You have to check for different properties, and there are unlimited numbers of angles that you can take, and so on. So you need to combine multiple images to assess quality. Not only different angles and levels of brightness and different color specters and exposure times, but you need to play with different settings and different angles as well. So this is an example. In the left, you can see the example of an image that is checking the functional properties, so how the light guide is guiding light. And in the right, you can see an image that is checking for decorative properties, which basically means if the piece is complete, and if there are no scraps on the side of the component, or any other issues with the component whatsoever. By the way, this is exactly the same component. One is taken in the black box when the lights are off. That's the left one. And one is taken in the black box when the lights are on to check the decorative properties. So once we have the images collected, and now I'll forget what I said about multiple images, and from now on I'll be talking about one individual image, and then I'll combine them all together when I will be talking about the machine learning algorithm at the very end. But once I take an image, the next step to do is to process the image so that computer can understand it, so that I have some features that are representing the image. And in this case, we are not dealing with computer vision. We are not dealing with image recognition. We know that there will be a light guide in the picture. The issue or the task that we are dealing with is that there will be some differences from the main trend, and there might be some defects, some new types of defects even unseen previously. And we want to make sure that we are able to detect even those from the data as they are coming in. So what we need is basically a set of features that are collectively robust enough to detect different kind of defects, be it a black dot or a line or different intensity of light or different color of light. But together, those features also need to be flexible so that they can be used not only for one component, but also for many other components, so that you don't have to learn or start from scratch whenever you are implementing the algorithm on a new production line. But you want to use the positive effects of transfer learning and take the existing algorithm and just start from there, so that you don't start from the very beginning every time you do an automation of a quality control on a new production line. So once you have those images processed, and each image is represented by a set of features that are describing what is in the picture in a very generic way, you do the standard data processing steps. So this is the standard drill that you see with any other machine learning that you typically rescale the image, rescale the features, and you rotate the feature space. You probably try to reduce the dimensionality of the feature space that you are considering for the machine learning algorithm to work as optimal as possible. And then we do clustering. Sorry. Why we do clustering is that we don't want to, because till this step, we are dealing with unsupervised, unlabeled train set, right? So it's unsupervised learning. We don't know anything about the images. We don't know which image is an image of an OK piece, and which of them are from images of defects. And in order to be able to prioritize and make use of our resources quite easily, and because we don't want to ask the company to label all the different, like thousands of images for us, thousands of components, and tell us which of them are okay and which of them are not okay. Because first, it will be extremely costly. And second, if there would be in the future a new type of defect, we wouldn't have it in the first place in the training sample. So our algorithms wouldn't know about this new defect. So the clustering tells us that basically there are several clusters of images that are very similar to each other, and they are very different from the images from different clusters. So very often you see one large cluster that is very often the example of OK pieces. That's what you want to see, right? The reason for this is that usually the scrap rate on those machines is around 10%. So roughly 90% of images are okay, and they are very often very similar to each other. So they fall into this big cluster that we call cluster 0 in this picture. And then you have a lot of other smaller clusters of images that typically have images that are different from the main trend. So the question now will be that we have clusters of images, and we want to ask someone to label those clusters so that we know which of those clusters are okay and which of those clusters are not okay. So the next step is something that is called anomaly detection. Why we do this when we have the clustering already in place is quite simple. We want to prioritize the work or the questions that we will be asking to the human expert. We don't want to waste their time. We don't want to ask them questions when we don't need to. when we already have enough information and we don't want to forget to ask any question that might be relevant. So we start with the clusters of images that are most different from the main trend. So they should typically contain defects that are very visible, clearly different from the main trend. Something is fundamentally wrong with the components in this cluster, and we want to start with them, and then we move closer to the main center of all the normal observations labeled by the model. Once we have this this prioritization, we need to ask the experts for their opinion. So how we do this is we created a simple feedback application that we basically tell them, this is the component. We ask you to evaluate individual anomalies, and we go one by one until we get the feedback about individual clusters of anomalies that we want to see. The reason why we ask here is that you might have an anomaly that is also a defect, but at the same time, there might be types of anomalies that are different from the rest of the OK pieces, but they are still OK. So it's not a functional, neither a decorative flaws in the image, and you can still consider the component to be OK. Once you do this, and once you have this implemented and it's running automatically on the production line, this application is spotting for new anomalies, new types of anomalies unseen before automatically, and is asking the questions to the expert for the expert opinion automatically. So you don't need to worry about a new type of defect if it happens anytime in the future. You will just be, or the expert quality controller will be asked to provide feedback on this new type of anomaly and potentially label it as a defect or not. Once we have this labels from the experts, and by the way, we don't have to. The beauty of the semi-supervised learning is that we don't have to ask the expert opinion on every single image in the cluster. We just need a representative sample from the cluster, or very often only one representative image from the cluster. If the cluster is homogeneous enough, you're reducing number of labels that you need to get from the experts, and of course, this is reducing costs for collecting or for generating the training sample quite significantly. Once we have all this kind of information, we train a simple binary classification model that is telling us which images, thanks to the features and thanks to the image processing and consequent modeling features, which of them are OK and which of them are not OK, which is the ultimate output from the model, labeling components as either OK or not OK. By the way, there needs to be a very high sensitivity of the model, because the big mistake that you can do is label not OK piece as an OK and send it through the production process further down the stream, and this will cause an enormous loss, enormous waste afterwards. So it's not that big problem to label not OK piece as not OK, but the other way around, it's a mistake that you don't want to make. Therefore, you need to have very, very, very high sensitivity of your model. Optionally, what the manufacturers also want to see very often is the classification of the defects. So in this case, they want to see how often was the defect just a black dot, which is caused by a bubble of air in the plastic component, or whether it was a scrap, whether it was decorative scrap, or was it a different kind of light color of the light that the component was or had. They also want to see what is the position or location of the defect in the image. So this is done by another set of machine learning algorithms that are then combined together to form some kind of a nice dashboard for the quality controllers. When this is implemented and when this is running automatically, by automatically I mean that no one touches the component from the moment it has been produced. It needs to be taken by a robotic hand, placed into a black box. All the pictures need to be captured. The algorithm needs to say whether the component is OK or not. This is the full automation. Otherwise, it doesn't make sense to deal with creating an algorithm if you don't, if you still need human touch, and if there still need to be someone who is standing at the machine and checking the quality manually, even if it's just moving the component from one place to another. So the business benefits of this full automation are obvious. First is that you have a very good quality KPI, which is different number of defected parts per million, where we aim for a number lower than 500. We also reduce quite significantly the workforce needed to do the quality control, so that you can use those people for more value-adding activities in the production process, and not just simply controlling whether what has been produced is okay or not. The inspection time is significantly lower. So imagine that you need to check the component manually. You need 10-20 seconds to do this. Inspection time by the AI algorithm can do this in a fraction of time. And once you start measuring the output quality of individual components on a standard basis automatically, you open a potential to even start analyzing the reasons why the machine is producing defects, and what is the optimal settings for the machine not to produce that many defects, and decrease the scrap rate even below 2%. Below 2%. And this is, by the way, the second case I'll be talking about now, which is AI-based machine optimization. Okay. So AI-based machine optimization. So as I said, the manufacturing industry is very much performance-oriented. Everything needs to run in an effective, efficient way. There is no room for waste, and you need to run everything optimally. So if you can imagine that if you are producing defects or faulty products, you are not running the machine in an efficient manner, because you need to rework. You have lost in time. You are losing costs for the material, and everything is just not optimal. And the OEE KPIs for the machine are bad, and everything in the business is falling apart. So what you want to do is to decrease scrap rate of the machine as much as you can. So that is at least below 2%, and very often that comes down from 10% or something like this. So it's a significant push that needs to be made. So that's the reason why you need to do the machine optimization. What is the business need for this? On the other hand, the state-of-the-art machines are very complex. So very often you need to set up hundreds of user parameters. You need to worry about sensor data that are measuring the humidity or temperature of the place where the machine is operating, and all of them are influencing the future the output quality of the components produced by the machine. And as you can imagine, this is not an easy task. If you have 100 user settings, the combinations of them are unlimited, and the yield engineers are basically not able, given the time constraints and restrictions, they are not able to find the optimal settings in their lifetime. So they need to rely on their experience, or just expert guess or qualified guess to find the optimal setting. However, there is AI that can do all this kind of stuff in a fraction of time, and it can find very easily what are the parameters or factors influencing the output quality, and that's why we are here today. So our solution is starting with the diligent data processes, because you need to combine data from different sources. I'll talk about this in a minute. And then we applied smart machine learning models, and followed by optimization tasks that are looking for the optimal solution, optimal setting for the machine, so that the scrap rate is at least as minimal as possible. And potentially you want to find the holy grail of manufacturing business, which is zero scrap rate, because when you are not producing anything that is bad, you are just in Valhalla, and everything works amazingly. So again, the first step is data collection. In this case, this is somehow tricky, because not many manufacturing businesses have already standardized data warehouse with all the data available, cleaned up and linked together. So you need, as a data scientist, you need to get your hands dirty. You need to get data about the settings of the machine, which is called process control data. You need to combine them with the quality output control data, telling you whether the components produced were okay or not. and very often you need to combine those data sets together with the data coming from the sensors that are measuring the context where the machine is operating, and whatever else might be relevant. The problematic part here is that those data sources are coming from completely independent systems, and very often no one has ever put them together. So there are no simple database keys that can be used to link the tables. But there are ways how to do this. However, you need to be very careful how you are doing this, and very diligent not to mess the data even more, because then, of course, no fancy algorithm would be able to detect what is the relationship between inputs and output quality of the machine. And by the way, that's exactly the step where tools like Ebula Connection are extremely handy, because they can deal with data from different sources, be it SAP system, be it Google Sheet or Excel files or CSV files coming from the machines directly. Right. Once you have the data collected, you need to process them in a step that is called feature engineering, which basically means that you would like to reshuffle somehow the data that you have on the input, so that it is way more visible what the relationship is. And for the machine learning algorithm, it is easier to detect the relationship between features and targets. So what you do here is a standard drill that any data scientists know by heart. You need to create a lot of features describing things like moving averages or time since last change, and then of course you can combine those features in steps that are again very standard in any machine learning. In any machine learning model, when you need to rescale them and normalize them, very often you do principal component analysis to reduce dimensionality, because the properties from PCA, features from PCA have much nicer properties for the machine learning model to spot the relationship between features and the target. So that's exactly what is happening here. This is the artsy part of data science. That's what I like the most. I disagree with a lot of people that are saying that you can just generate hundreds of thousands of features and then you'll find the best one there. I believe that you need to start with a set of hypotheses, what exactly you're looking for, and then of course a machine can help you generate a lot of features around this. But the hypothesis, what exactly am I measuring and what exactly should I be looking for, is very useful as a starting point at least. And then obviously once you have a clean data set that is telling you these were the inputs, this is the output quality, you can train an algorithm that will tell you what is the relationship between these inputs and outputs. So in other words, it tells you what is the expected scrap rate for individual settings in a feature space. What you can do with this information is that it can be followed by an optimization task, which help you to find minimum and maximum. Obviously, you're looking for the minimum scrap rate. So what is the minimal scrap? What is the setting to reach minimal scrap rate? And not only the optimal setting, but you also need to have some kind of lower and upper boundaries for individual user setting parameters. Because it's not easy to set a temperature right to let's say 260 degrees, because there will be some thermometer or heater going on and off based on the temperature. So the parameters are oscillating, and therefore you need to provide something that is called a process window, which is exactly the lower bounds and upper bounds for individual user settings. The AI part of the solution is also providing an information like or hypothesis for what settings should be tried in order to find the global optimum. Because very often, if you have a parameter that or user setting that nobody has touched, or it's only used within a certain range, and the algorithm is telling you that probably the optimal might be behind this range that has been tried in the past. It will also tell you the hypothesis what to try, and then the algorithm is actually self-learning, and it's creating a smart design of experiment what to test in order to find the global minimum of the scrap rate and what is the settings for this global minimum. Now, once this is done, you have to persuade the yield engineers that the setting that the machine learning algorithm or the AI is suggesting is actually superior to their own opinion, and you have two conditions to meet if you want to succeed in this task. First, that your algorithm needs to operate with an incredibly high accuracy, because if the algorithm is not accurate, the trust in the algorithm will fall apart immediately. And the second one, even if the algorithm is working well, people have a tendency not to trust something they don't understand, and they have a tendency to overrate their own abilities. And therefore, you need to show the yield engineers why the algorithm is recommending what it's recommending, for which we realized that a simple effect analysis can work quite well. So you have a buy-in from the yield engineers, and they very often can come back with a nice and useful hypothesis for how to improve the AI solution even more, because they have hypothesis what to measure. They might place a new sensor here and there, and it will improve the accuracy even more, and very often significantly. Once this is fully automated and it's running on the machine, the business benefits are quite nice. First of them is that if you decrease the scrap rate below 2%, your OEE KPI for the machine is also increasing. Very often we've seen that the OEE can go above 90%. A 90% range, so that's quite high, I would say. The obvious consequence of this, if you don't have to, if you're not producing that many defect products, defect components, you're not wasting any time of the machine, or you're wasting less time of the machine and also less material. So you have enormous savings on this side as well. And very often we were able to even reach the 0% scrap rate, which has a very nice side effect, that is making the quality control completely redundant, because you don't have to check if you don't have to check for defects if there will ever be if there will never be any. So that's why the zero is a beautiful number, as the Japanese manufacturing engineers are saying very often. Okay, that's it from my side. These two case studies. Thank you very much for listening, and I hope you'll find this interesting, and maybe you will get in touch, and we might do a project together to show you and demo this on your data, and do it as a POC in a matter of days, so you will see the benefits it can have for you on your own data quite soon.
Well, thank you for listening. Thank you to Adam and Alok. As mentioned, if you have any questions, please submit them, and we'll be emailing you the answers and any updates we can sort of supply with those. Also, we'll be attaching the link to some more future webinars. Well, thank you once again, and thank you, Adam.
Thank you very much.
Enjoy the rest of your day, everybody. Bye.
Bye.